Somewhere right now, a family is signing a mortgage. 30 years, fixed rate, monthly payments that will consume a significant portion of every paycheck they earn for the next 3 decades, in exchange for the right to live in a structure built from materials chosen not because they are the best available, but because they are the most profitable to manufacture, distribute, and install. They did not choose this. They were not presented with alternatives. They walked into a system that had already decided what their home would be made of, what it would cost, and how long they would spend paying for it. And that system worked exactly as it was designed to work, moving money from the people who need homes into the accounts of the people who build them, finance them, and supply the materials that go into them. But there is a wall that changes that equation completely. Not a wall made from a new material invented in a laboratory. Not a wall that requires specialized equipment or licensed installation. A wall made from a steel mesh frame, tensioned cables, and mortar. A wall that costs $15 to $30 per square meter in materials. A wall that can be built faster than conventional masonry, with less weight, less waste, and less structural demand on the foundation beneath it. A wall that the construction industry has had every financial reason to ensure you have never heard of. What the construction industry charges you for. Before we talk about the solution, we need to talk about what you are actually paying for when you pay $800 to $1,500 per square meter for conventional construction. You are paying for concrete, which requires quarried aggregate, cement production that is among the most carbon-intensive industrial processes on Earth, water, and the equipment to mix, pour, and cure it. You are paying for steel reinforcement, which requires mining, smelting, and fabrication. You are paying for brick or concrete block, which requires clay extraction, kiln firing at high temperatures, and transportation from the manufacturing facility to your building site. You are paying for the labor of skilled tradespeople whose certifications, tools, and professional overhead are factored into every hour they bill. Each of these costs is real. The materials are genuinely expensive to produce. The labor is genuinely skilled. The system is not fraudulent in the sense that the costs are invented. It is fraudulent in the sense that these are not the only options. The cost of conventional construction is not the cost of shelter. It is the cost of a specific way of providing shelter, a way that happened to become standard because it served the interests of the industries that supply the materials and perform the work, not because it was the best possible way to build a home. The alternative that those industries would prefer you not explore costs $15 to $30 per square meter in materials. The difference between those two numbers represents the profit that disappears when you build differently. The wall that should have changed everything. The system is called ferrocement, or, in its more refined modern applications, tensioned mesh construction. The principle is elegantly simple, and the performance it delivers is, by the standards of conventional construction, almost impossible to believe until you see the engineering behind it. A ferrocement wall begins with a structural frame, typically lightweight steel rods or pipes arranged to define the wall geometry. Over this frame, layers of steel mesh are stretched and secured under tension. The tension is critical. It is what transforms a flexible mesh into a structural element. When mortar is applied to both faces of the tensioned mesh, penetrating through the openings and bonding to the steel, the result is a composite panel in which the steel mesh provides tensile strength and the mortar provides compressive strength and surface integrity. The wall that results from this process is thin, typically 25 to 50 millimeters, compared to 200 to 300 millimeters for conventional masonry. It is light, placing dramatically lower loads on foundations than brick or concrete block construction. It is strong, with a surface hardness and impact resistance that exceeds conventional plastered masonry in most testing. And it is fast to build, because the mesh and mortar system eliminates the time-consuming process of laying individual bricks or blocks in mortar courses. The material cost is where the argument becomes overwhelming. Steel mesh and mortar are among the cheapest construction materials available anywhere in the world. A square meter of ferrocement wall, including the mesh, frame, and mortar, costs $15 to $30 in materials in most markets. A square meter of conventional brick masonry costs $80 to $120. A square meter of concrete block construction costs $60 to $150. The difference is not marginal, it is between 70 and 90%. For the walls of a modest home, the difference between ferrocement and conventional construction in materials alone represents tens of thousands of dollars. That is the money that stays in your pocket instead of flowing to the concrete block manufacturer, the brick supplier, and the masonry contractor. The history the industry quietly buried. Ferrocement was not invented last year by a startup looking for venture capital. It was invented in 1848 by a French engineer named Joseph-Louis Lambot, who used wire mesh and cement mortar to build a boat that he exhibited at the Paris exhibition of 1855. That boat, built over 170 years ago, was still floating and structurally sound when it was last documented. In the 1960s and 1970s, ferrocement attracted serious attention from international development organizations as a low-cost construction technology for housing in developing countries. The United Nations Food and Agriculture Authority extensively researched and promoted ferrocement boat construction as a low-cost alternative to timber and fiberglass for fishing communities worldwide. Hundreds of ferrocement boats were built and documented, demonstrating structural performance, durability, and repairability that conventional fiberglass and timber construction struggled to match at equivalent cost. The engineer Pierre Luigi Nervi, one of the most celebrated structural designers of the 20th century, used ferrocement extensively in his work, demonstrating that the material could produce structures of extraordinary elegance and span that conventional reinforced concrete could not approach at equivalent cost and weight. His ferrocement structures from the 1940s and 1950s are still standing today, celebrated as masterworks of structural engineering. In the 1970s and 1980s, researchers at the University of California, Berkeley conducted extensive testing of ferrocement as a housing material, documenting its structural performance, durability, and resistance to seismic forces. Their findings were consistently positive. Ferrocement walls demonstrated crack resistance, ductility under seismic loading, and repairability characteristics that compared favorably with conventional masonry in every category that matters for residential construction in earthquake-prone regions. The technology was validated, the performance data existed, the cost advantage was overwhelming and documented. And yet, in the decades that followed, ferrocement construction remained on the margins of the housing market in the developed world, practiced by a small community of owner-builders and alternative construction enthusiasts, while the mainstream construction industry continued building with brick, block, and concrete frame. Why it stayed on the margins? The explanation for why a technology with such compelling cost and performance advantages failed to displace conventional construction is not mysterious. It follows the same pattern that explains why every other affordable, accessible building technology has remained marginal in markets dominated by large construction interests. Ferrocement does not support a supply chain. Conventional construction materials, concrete, brick, block, steel reinforcement require manufacturing facilities, distribution networks, and supply chains that represent enormous capital investment. The companies that own those facilities and networks have deep relationships with the builders who use their products, the regulatory bodies that specify materials in building codes, the banks that finance construction projects, and the professional associations that train and certify the contractors who specify and install materials. Ferrocement requires steel mesh, which is a commodity product available from dozens of manufacturers.
Ferrocement requires steel mesh, which is a commodity product available from dozens of manufacturers. Mortar, which is sand, cement and water, available everywhere, and labor that does not require specialized certification because the application technique is learnable without years of training. There is no proprietary product. There is no manufacturer whose profit depends on widespread adoption. There is no supply chain that benefits from ferrocement becoming the standard. Without a powerful commercial interest advocating for its adoption, ferrocement had no pathway into the building codes that govern what gets built. Building codes in the United States, Europe, and Australia include detailed prescriptive requirements for concrete frame construction, masonry construction, and wood frame construction, because those are the systems that industry pushed to have specified. Ferrocement residential construction has no comparable prescriptive code pathway in most jurisdictions, meaning that a homeowner who wants to build with it faces the same variance and engineering certification process that confronts any unconventional system. The barrier is not technical. The technology works, and the evidence proving it works goes back 170 years. The barrier is commercial. The system rewards what can be sold at scale by large manufacturers, and ferrocement cannot be sold that way. So it was not adopted, not because it failed, but because there was no profitable infrastructure to adopt it through. What $15 per square meter actually means. Let us translate the material cost advantage into terms that make the financial implication concrete. A modest home of 100 square meters of floor space has approximately 150 to 200 square meters of exterior and interior wall surface. At conventional construction costs of $100 to $200 per square meter for walls, the wall cost alone is $15,000 to $40,000. At ferrocement material costs of $15 to $30 per square meter, the same wall area costs $2,250 to $6,000 in materials. The difference is $12,750 to $34,000 for the walls of a single modest home. That is the money that stays in your pocket instead of flowing to the concrete block manufacturer, the brick supplier, and the masonry contractor. Over the entire construction of that home, the savings compound. Lighter walls mean simpler, less expensive foundations. Less material weight means lower transportation costs. Faster construction means lower labor costs. The total cost reduction compared to conventional construction for a complete owner-built ferrocement home has been documented at 60 to 80% in multiple independent studies. A home that would cost $150,000 to build conventionally can be built with ferrocement for $30,000 to $60,000. A family that builds their own ferrocement home, owner builds the walls themselves and sources materials at commodity prices, can complete a structurally sound, durable, comfortable home for $20,000 to $40,000 total. That home requires no 30-year mortgage. The interest payments that would have consumed $100,000 to $200,000 over the life of a conventional home loan simply do not exist. The financial liberation that represents is not a marginal improvement in a family's economic position. It is a fundamental restructuring of their relationship to the housing system. The strength they never told you about. One of the persistent objections to unconventional construction materials is structural performance. People who have lived their entire lives in brick and concrete homes have a visceral confidence in the solidity of those materials and a corresponding skepticism for alternatives that look different or use less material. The engineering data on ferrocement does not support that skepticism. Ferrocement walls in standardized testing demonstrate compressive strength comparable to conventional masonry. Their flexural strength, resistance to bending forces, exceeds conventional unreinforced masonry because the mesh network provides continuous tensile reinforcement throughout the wall section, rather than only at discrete rebar locations. Their impact resistance, the ability to absorb and distribute point loads without catastrophic failure, is superior to conventional masonry because the mesh network distributes stress across a large area rather than concentrating it at the point of impact. In seismic testing, ferrocement walls have demonstrated ductility characteristics that conventional unreinforced masonry simply does not possess. Where a brick wall under seismic loading cracks and collapses, a ferrocement wall of equivalent thickness deforms and distributes the seismic energy through the mesh network, maintaining structural integrity at load levels that would have produced catastrophic failure in conventional masonry. This is why ferrocement attracted serious attention from earthquake engineering researchers in the 1970s. In regions where seismic risk is a primary determinant of building safety, the performance advantage of ferrocement over conventional masonry is not marginal. It is the difference between a wall that falls and a wall that stands. The construction industry that sells you brick and concrete block is not selling you the highest performing option available at your price point. It is selling you the option that its supply chain is built to deliver. The performance data says something different. Building your own. The accessibility of ferrocement construction to owner-builders is one of its significant advantages and one of the things the construction industry least wants to acknowledge. The skills required to build a ferrocement wall are learnable without professional certification. Cutting and shaping steel mesh requires basic metalworking tools available at any hardware store. Tensioning the mesh to the frame is an understanding of the principle, but not years of training to execute. Applying mortar to a tensioned mesh surface is a skill that most people can develop to an adequate level within a day of practice. The tools are basic: wire cutters, pliers, a cement mixer or a mixing trough and a shovel, a plastering trowel. None of these items require specialized sourcing or significant investment. The materials are available everywhere that construction happens. Steel mesh is produced globally and available from building supply companies in every market. Portland cement, sand, and water are the most widely available construction materials on Earth. There is no proprietary component, no licensed product, and no supply chain that can restrict your access to what you need. An owner-builder who commits to learning ferrocement construction has access to a complete housing system that costs a fraction of conventional construction, can be executed without professional contractors for the primary structural work, and produces results that have been validated by 170 years of documented performance. The system that profits from conventional construction would prefer you not know this. The building code that was written by people connected to that system has made it harder than it should be to build this way. The mortgage industry that profits from home loans has no product to offer someone who builds for $30,000 in cash. But the mesh is on the shelf. The cement is at the yard. The technique is documented and teachable. And the engineering performance data accumulated over 170 years of application says clearly this wall works. They buried the evidence. They built barriers around the alternative. They made the cheap option hard to permit and the expensive option the default. Now you know what they buried. The question is what you build with that knowledge.